Good morning, everyone. So welcome to the second part of this induction training organized by IIT-Kanpur in the partnership with iForest, NEERI, IIT Madras, IIT Roorkee, under the aegis of National Knowledge Network, which is an approved think tank by Government of India. As you know that many of you attended the first part of the induction training, which basically covered some of the basic ideas behind National Clean Air Program, monitoring, impacts, and many other associated things in a very concise way. Now, as you know, today, that is 21st of February, we are starting the second component of this induction training, which is going to be focused towards city action plan and third-party audit. So as part of this, I'm going to talk about some of the basic principles of source apportionment. What do we mean by source apportionment? The entire lecture will be more focused towards understanding source attribution, source apportionment of PM2.5. Briefly, I would also mention one result that has just come out from Delhi related to source apportionment of volatile organic compounds. So let me share my slides. So this is my first lecture as a part of this induction training on city action plan and third-party audit. I'm Sachidanand Tripathi. I'm a professor at Department of Civil Engineering. So let's start with the very basic idea behind source apportionment. Basically, source apportionment is major sources that contribute to the PM2.5 that we see in the ambient atmosphere. So basically what it says that it is a practice, right? So it's important word in the practice because it is practiced by practitioners of deriving information about pollution sources and the amount they contribute to ambient air pollution. So it could be for particulate matter or it can be for gases. And there are three broad ways by which one can do source apportionment. One is by using the emission inventories. Second is, which is basically you try to track from what is emitted from the source. And third is that you create or get information from, let me also get this spotlight on. And third is that we try to collect samples of gas or particulate matter at receptor and then try to go to the sources from that. So in a nutshell, this cartoon on right shows this entire set of procedures that is required to complete the source apportionment practice, that is the source information for particulate matter or gases. So what you see that here you have a city, you first try to choose locations and that where you want to collect the data of particulate matter or gases. That is what is shown here, that you have different kind of particulate matter samplers, high volume or low volume or some other kind of sampler you use. Once you have collected it, then you are basically going to analyze it. What kind of analysis one does? One is that you try to weigh the amount of particulate matter which is collected on the filters, because these samplers use filters, some kind of media on which particulate matter is deposited, and then that is carefully kept secure and then brought into the analytical laboratory. In fact, if there is a timeline between these two steps, then one has to take utmost care in storing them in freezer or so that the volatile material does not get lost. The second part of that is that once we have understood that what is the total mass of particulate matter that is deposited on filter, and one does chemical analysis. So there is a variety of chemical analysis one can do related to iron, organics, metals, etc. that we'll see in subsequent slides. And after that, this information is fed into the type of models you want to use. So it becomes an input data. Okay, for PM2.5, for PM10 or PM1, most of the time we are interested in doing the source apportionment for PM10 or PM2.5. So this information is then fed into these models, and then the model output is looked at carefully, analyzed, and then that is what this output actually gives you factors or sources. That what it shows that, well, for a given, let's say, particulate matter X microgram per meter cube sample, let's say that this blue side, it is telling you how much of X microgram per meter cube is contributed from vehicular emission. It shows that 70%, just for an example. And the remaining 30% might be coming from other sources. So all that basically would be given from the output of this model. And if you add it all, then that should sum up to the total particulate matter on an average as a whole, which is sampled at this site. Okay. So how are we go about it? Basically, we need to do source apportionment because the policymakers require quantitative information about sources so that they get an idea that what are the sources which are contributing to what we see or measure in the ambient air. Second is that we also want to, or they want to understand, the regulators and policymakers, that why particulate matter or gases are exceeding the standard. So when it is exceeding the standard, it could be due to certain sources contributing excessively, right? If all of them are contributing in a way that basically leads to, let's say, 60 microgram, which is the standard for India, then we don't have any issue. But if it becomes, let's say, 65, 70, 80, 100 or something like that, then one needs to 40 microgram is contributed from which sources, so that one can go after those sources and try to mitigate or plug them. Third also is an idea, because you are sampling at different sites, depending on how many samples you have or how frequent or how dense your time series is of the sources, source factors you are getting, you could also reasonably estimate that the sources are, which are the location from which these are contributing at the receptor. Okay, so that's the third part of that. Now, just to extend that, you can get what is the geographical locations of sources in that city, which is contributing to the ambient air. You could also get what is coming from outside that political, let's say, entity. So maybe between two states, one could estimate how much is coming from the other state. Many times we know that in Delhi, that there are contribution to Delhi PM2.5 from the stubble burning that happens in other states surrounding Delhi. So one could get also the estimate of that. And then if you look, for example, a little larger region of, say, Gangetic Plain or Indo-Gangetic plains, then using similar type of approach where you have actually sampled it at various locations, starting from, let's say, Punjab to West Bengal, which forms the Indian side of Indo-Gangetic Plain, you could also get an idea about the contribution to PM or gases, which is coming from the neighboring countries. Then, based on these information, generally air quality action plans are designed. Okay, that is, action plans means how and which sources are frequently causing accidents. So you want to do something about it. Whether, depending on the meteorology, there is a particular geography from where plumes emanate and contribute or make city polluted. So you have to probably relocate. So many such things are done. And then certainly it also tells you an idea about the remediation, the kind of measures you are taking to improve the situation, how effective they are. Okay. It also helps to refine emission inventory, because emission inventory is a forward approach where you are able to quantify the strength of sources, and then using that you want to predict what concentration and composition you expect at receptor sites. Now you see that between the source and the receptor, there are several processes, which includes dynamic, physical, and other chemical processes, which is quite complex. So therefore, it's a somewhat non-linear relationship between emission and ambient concentration and ambient composition. So if you have that information at receptor, and if you are getting the similar information using using models which are relying on the emission inventory, you could compare the two and try to minimize the errors in emission inventory. Okay. And finally, you can also understand what is the movement of the pollution. So many times we know that during winter, the pollution moves from northwest to southwest, and finally it enters into Bay of Bengal through West Bengal. So these kind of outflow one could also understand by doing the well-designed source apportionment studies. So as we said that there are three broad methods, but under those three broad methods, there could be other methods which are basically sub-methods or sub-categories, which could be explorative, that is basically it doesn't use any detailed method, rather it's more exploratory in nature. We discussed about emission inventory. That emission inventory, once you have, then you try to feed that, implement it in some kind of a forward model, which could be a metrology coupled with chemistry model. And there is also an idea that you have done modeling and then you try to inverse it. Okay, using model and some measurement to try to invert it and then use that. Then there are also some people have started using, of course, artificial neural network, which is a kind of AI. Then you have very well-known Gaussian models, which is again, you start with the source and then using the Gaussian approach, you try to predict, given the atmospheric turbulence and wind speed, you have certain criteria, you try to predict what is the concentration at the receptor site, but it will not be able to tell the contribution from various sources because it does not account for the chemistry which is happening in the atmosphere. And then of course you have receptor models, which we said that what you collect, the information, the fingerprint you get at the receptor site, and then you try to invert that, which tells you again the sources. So you see that then the source oriented models, example of that is, for example, WRF-Chem or WRF-Chemex, where you have a meteorological driver coupled with a chemistry module. And this is a forward approach. This is going to give you concentration at the receptor. Okay. The second approach is, of course, receptor oriented models, where you have collected information at the receptor side, but this also many times require source profiles. Source profiles implies that what is the nature in terms of chemistry and in terms of the relative abundance of particulate matter and gases, which is specific to a particular source. Particular source can be an incinerator, or it could be a specific industry, let's say fertilizer, or a pharmaceutical, or a smelter, or it could be for a mobile source, for example, a car or bus or something, or it could be for a burning kind of source. See, remember, each of them would have, when the plume is not mixed with other sources, it will have a very specific profile. That is, the particulate matter which is coming from it will have a very specific size and will have very specific chemistry. This is required for receptor-oriented models. And then what you see that from this also you can go to sources, and from source-oriented models also one could come to the sources. Okay, you see these are two very different approaches, but both of them are important in order to make substantial progress in our understanding of sources that are basically that contribute to the particulate matter or gases which we measure or see in the ambient atmosphere. So you see, receptor models is something what we are going to discuss in more, because in practice, because it is based on measurements, generally, as of now, policymakers or practitioners tend to use this more. Okay. So what you do here is that whatever you measure at a site, which is called receptor, then you do certain kind of analysis, and from there you use a multivariate analysis. That is, it's a multi-variable model which is used to solve a mass balance equation. Okay. Certainly, it follows the assumption of mass conservation. In reality, of course, at different stages, some will have to have these assumptions applied all the time for the success of this model. Okay, so there are also in receptor models currently, there are a whole genre of models that people are using. For example, there is a chemical mass balance model, which has become slight now old. Then there is a multivariate model. There's a whole group of that called unmix. Now, recently, US EPA and others have started using positive matrix factorization, which has become a more staple tool for using the receptor-based modeling. And multi-engine, or more precisely multi-engine 2, is a little, you can say, refined version of PMF, which also people have started using, which is in some way, it has a greater possibility to finally arrive at an environmentally intuitive solution. Okay. So how do we go about it? We need to get certainly, when we measure at the source, we need to get certain source signature. That is what you see here in this cartoon, which was probably part of the paper published in Atmospheric Research. The reference is given here at the bottom. But you see the wind is coming, and different type of particulate matter in terms of their varying chemistry are emitted from various sources. So you see there are biomass burning sources, there is land or dust coming from crustal elements, then you have something, you know, where the solid wastes or the municipal wastes are burned, that's a waste incineration. And then this is here, then you have industrial, variety of industries, and then you have vehicular sources, and finally you have also something coming from marine sources. You see, each of them have very different chemical signature. You see, biomass burning would have levoglucosan, which is a kind of polyaromatic hydrocarbon. Then it can have manosan, it has anthracene, and then it can also have some kind of ammonia and potassium. If you look at the crustal sources, the particles which come from them would have these crustal elements: silica, aluminum, iron, calcium, magnesium, etc. Which is very distinct from this. Then what you see, if something is coming from waste incineration plant, it would have lead, zinc, arsenic, bromine. Likewise, if you are getting a PM from industrial emissions, then this would carry with itself nickel, chromium, cobalt, cadmium, and arsenic. And from vehicle, what you get copper, lead, zinc, barium, iron, aluminum, potassium, and calcium. And from sea salt, of course, you have sodium and chloride. That majority of salt is composed of that, and you might have some other salt. So you see that a couple of these two are natural and all other are basically anthropogenic sources, that particulate matter coming from them or gases generally have a very distinct chemical signature, which is very specific of that source. And now as things come out, they can undergo a variety of microphysical processes, which is called, sometimes gases can form and then they can give rise to the particulate matter formation. Then you might have also aqueous chemistry happening, because most of particulate matter have some water in that, and gases can dissolve and can give rise to formation of salts. The particles which form can grow by further condensation of gases, or they can also interact with each other, which is called coagulation. And after all that, you can have that what you sample at the receptor site. So when you sample something at receptor site, that particulate matter would actually be a mixture of all that. So your goal is to then from here, how to, using these signatures, how to get to these sources, and also try to get a reasonably accurate idea of the relative contribution, or in fact absolute contribution from each of these sources to what you sample here. Okay. So this is now next few slides I have borrowed from one review paper which has just come out with us as co-author. This paper actually gives you a comprehensive idea about the current status of source apportionment of ambient aerosols over India. Okay, so you have actually two broad sets of processes, or broad set of methods, to be more precise, which you could use now to do the source apportionment using the receptor approach. One is offline, which is basically things are collected on filter. First you target the size, that's PM2.5 or PM10, then according to the need and subsequent analysis, you choose filters, and then you also, according to the need, you choose how many number of sites and how often you want to sample. For example, if city is large, you might need more sites to get a actual representative, because for a large city, the source contribution may vary from site to site. Second is, how frequently do you want to sample it? That again depends on what is the ambient concentration and some other factors. On the other hand, now a real-time source apportionment has also started gaining some traction in the country. There also, again, you start with target PM, use what online monitor you want to use, and likewise whether how many number of sites you want to do. Temporal variation is not an issue here, because they generally provide you information at a very high temporal frequency. So remember that, whereas in this case, you are collecting filters, storing them, and then doing the lab-based analysis. Here is all online. All the chemical information you get in real time using these kind of monitors. Now, what kind of chemical analysis you do with the offline technique? You can do the gravimetry. We talked about that earlier, which gives you the mass of particles. Then you can use these different sets of instrument, either this GC or HPLC or GCMS, etc., to get accurate information about organics. Then you can use this AS or ICP, induction coupled plasma, or some other such methods, or XRF, X-ray fluorescence method. These can give you accurate information about elements, metals. Then you use ion chromatograph for getting the water soluble ionic species, and then for organic carbon and elemental carbon, you want to do OC and EC analyzer. And this organic basically is for getting the polyaromatic hydrocarbon detected. Here, what you do, you can either go for PM1 or 2.5, and NR means non-refractory, because most of these online instruments give you information only about non-refractory particles. For the refractory particulate matter, that is metal and black carbon, you have to complement it with some other instruments. So for example, you can use exact for metal, which gives you real-time metal analysis, and it works on the principle of basically XRF. Likewise, for organic carbon, elementary carbon, you could use either athelometer, or you can certainly get OC-EC analyzer. Remember that this OC becomes redundant because OC can also be gotten from this online instruments. So both these sets can then be fed into receptor models, what we discussed earlier. But the only thing is that whereas here there will be time lags between these steps, this actually can be all done in real time, and there might be a small lag in order to first train the model. So maybe after a week of sampling of the data, you can start doing the receptor modeling. Now, what kind of generally some organic tracers one uses to get more accurate idea about the sources? So what you see, there are two sets of organic markers one could use. One is non-polar, another is basically falls in polar. So in non-polar, you see, one can use alkanes, which are long chain compounds, for biogenic and something what is coming from petrogenic sources. If you want to get the fossil fuel, then one has to go for isoprenoid hydrocarbon. Okay. Likewise, for regular emissions and coals, one can go for hopanes. The polyaromatic carbons, hydrocarbon pH, as we discussed earlier, are very important. Like levoglucosan is an important pH, is a very important fingerprint for combustion tracers. And then there can be specific markers. For example, is mentioned here, piscine is for coal, nicotine is for tobacco, and etc. etc. In polar, you could use alcohols and sterols for wood smoke. So see, this is a very specific source, and you are using a very specific kind of organic compound. And likewise, there are variety of those which you could use to basically pinpoint the source you want to decipher. For example, isoprene oxidation products generally show that the secondary organic aerosols are coming from biogenic. That is, they are coming from the emissions from trees, forests. Okay. Likewise, how do you do this? Water soluble inorganic salts. So what are various water soluble inorganic salts, and what kind of sources do they show? Right. So you see that starting different color arrows shows the metals which are enclosed in that colored box. So for example, sodium, magnesium, calcium, chlorine, and this potassium, they all basically show the dust, soil dust, mineral dust, or root dust. And what you see, what comes in this blue color circle or oval basically shows sea salt. Something is coming from sea salt, which will have magnesium, chlorine, calcium, potassium, and sulfate. Then what you see in green is something which is coming from fossil fuel combustion, and that would have calcium, potassium, sulfate, nitrate, and ammonia. Right? Likewise, in orange box, which shows secondary inorganic aerosol, those kind of inorganic aerosol which form in situ in the atmosphere would have sulfate and nitrate. Okay, and they also, what you see, if you make it, and then also ammonia. Right, within this yellow, there are three things: sulfate, nitrate, and ammonium. Out of that, two of them, sulfate and nitrate, may come from industrial emissions as well. And finally, what you see this magenta or violet color shows that presence of potassium, ammonium, and phosphate could come from organic decay and decomposition, animal farming, etc. Okay. And there is also one more. This dark blue is only showing the presence of chlorine ion, and that can come from uses of these PVCs. If you burn these PVCs, that can give rise to chlorine. So if I put overall that this dash line, this could show a variety of sources, that is biomass burning, residential fuel wood burning, agriculture waste burning, open burning on streets, wildfire, incineration. Okay. So with all that, actually what you are getting is a mix of very complex sources. Separating them out requires accurate analysis, chemical analysis, and good understanding of model and solid interpretation of data. So let's just see that what is the current spread of source apportionment which already exists in this country. So you see, if we try to divide that all the source apportionment studies in the country, you see 34% of them has been done on PM10, and roughly same is done on PM2.5. And most of them, you see, as of now, have used offline methods. Okay, the first method what we discussed before. Only as of now, 1/4 studies, source apportionment studies, use the real-time approach. Okay. Now, if you see how much, what kind of data related to water-soluble inorganic salts which we have used in the source apportionment studies conducted in the country. So you see 41% of them have used elements, water-soluble inorganic salts, and carbonaceous. So that is EC and OC. Only elements also, some studies have done source apportionment using that. That means it's limited source apportionment, but they have done it using only elemental data. Likewise, some of them have used only element and water soluble, these ions, which are 30%. Okay, so there are basically some studies have used some different sets of chemical fingerprinting to arrive at the source apportionment. Remember that they would have some limitation, because if you increase the fingerprinting, that is, if you do more and more chemical analysis, you have chances to get better and better information and granularity of the sources. Now, this map over India shows for 4, let's say, broader regions for PM2.5, that how they are speciated. Okay, so this one is Delhi, this is Bhopal, this one is Mumbai, and this is for Nagpur. And you see different color shows that contributions from different kind of species. Broadly speaking, what you see, one thing stands out, that organic is a big contributor, which is 19% in Delhi, is 37 to 40% in Bhopal, of same order or similar to that is for Nagpur and as well as for Mumbai. Now, if you look for black carbon, again, black carbon contribution is very high, but it is highest in Bhopal, which is going about 16% compared to other 3 places. And the third major contributor is basically sulfate. Sulfate also contributes somewhere from 9 to as high as 18% over these 4 cities where that kind of information is available. Now, this same information now is given for PM10. So what you realize that for PM10, we have more number of stations where chemical speciation and therefore source apportionment information is available. Okay. So what you again see that this is available for Delhi, Kanpur, Varanasi, Tezpur, Kolkata, Hyderabad, and Mumbai. what you notice that generally speaking, that percentage contribution of OC to PM10 has reduced or is somewhat lesser than in terms of what we see that for PM2.5. But you would certainly notice that contributions of these metal elements, that is calcium, magnesium, aluminum, etc., has gone up. It has gone up to from 6 to 12, 13% for all these places. You could notice that. Look at calcium is about 3, 4% or 6% here, compared to if you look at the previous one, you see that they are just 2 to 3%. So altogether, elemental contribution is about probably from 6 to 10%, where for PM10, it has gone more than 10 and up to even 15% sometimes. Okay. This plot shows that what is the basically fractional contribution. So this is a donut plot, and within the donut in the center, it shows that across what is the contribution of source apportionment studies which are done over Delhi as a fraction of all studies done over India. So that means about 2/5 of all the studies done in India has been conducted over Delhi. It's 37%. You see, likewise in Gangetic Plain, it is 29. So that's about 1/3, a little less than 1/3, has been conducted over Gangetic Plain. Now, if you look at Central India, it has a meager 3%. Peninsular India still has about 20%. Eastern India has 1/10, 10%. So Western India and Central India actually has a lot less contribution in terms of the source of apportionment studies conducted over India. Whereas Delhi, NCR, and IGP put together constitutes about somewhere 70%, that is more than 2/3 of all the source apportionment studies conducted over India. And then if you look into the outer part of this, it shows that how within Delhi, basically, these studies have been distributed. So within Delhi NCR, you see most of them has been done in Delhi. Very small part is actually in Gurgaon and likewise here. And then in IGP, it shows that what is the fraction. So if you make this outer circle 100%, so this tells out of 100, what's the percentage done for different cities or different part of IGP. So you see 1/10 is done over Agra. There is a relatively large number done over Kanpur, and then there are some studies done over different part of IG planes. Okay. Likewise, this one shows that source apportionment studies again done for different type of PMs, PM10, PM2.5, and PM1. So if you look here, in this one, you see over Delhi NCR, most of studies are done over PM2.5, which is 1/3, and almost equal is for PM10. And this light blue shows real time. What is the fraction of all source apportionment studies conducted over Delhi has used a real time method? So what we see that over Delhi NCR and in Western India, the uses of the real-time measurements are increasing, both in Western India in terms of fractional percent and Delhi NCR. There is good use of now real-time instrumentation, which also is significant in IG plane. But if you look at Central India and Eastern India, as of now, contribution of or use of real-time instrumentation to do source apportionment is still not there. Okay. So now from here, I will discuss more about the approach, that is the real-time source apportionment, because the paper I just showed, the review paper and many other reports, and there is enough literature now for us to get a good idea about that offline approach of source apportionment. But what I am going to argue here is that for baseline, offline approach is required. But for an effective air quality management, real-time source apportionment is a way forward to provide a dynamic feedback or input into the policy making. And that is what now currently is being practiced in several parts of the world. So what you see that if you look at the case of Delhi NCR, you see Delhi NCR from October to February, air quality can go from very good to severe within a week or 2 weeks, and it can stay fluctuating in that way. So because these offline methods, they require certain amount of data, and because of the limitations of the sampling, you can only collect information at a time scale of few months over a season, so that you can have minimum number of samples, which is statistically good sample size to run your receptor models. Basically, these approaches, offline approaches, can only give you seasonal information about source apportionment. Second, because you need to have at least 60, 70 to 80 filters. Therefore, only after that much information is available, then you can start doing the chemical analysis and you can run the model. So generally, if you are doing it for more than one site, this easily can take from few months to more than a year before you start getting the information. And by then, actually, there are many things that would have helped, some information that would help to get some meaningful policy interventions done, is not possible with that kind of method. So, and third, there is also a good bit of uncertainty in terms of granularity and getting the secondary PM apportion into sources, both for secondary organic and secondary inorganic. There is a I'm going to talk more about this real-time approach and how it can provide you some very interesting results. Okay, so this is what one work which we did in Delhi some time back, where there were three sites were chosen. One is what you see, this IITM site, which is slightly upwind over map of Delhi and city. One is the central site, IIT Delhi, another is downwind, the Manorashna. And using this real-time instrumentation, we could resolve their chemistry for PM2.5 at 2 locations. These two at Manorashna for PM1. And their composition is given here in the pie. And then it is further, the organic has been very kind of sufficiently accurately further speciated into these 3 sets of important factors, which are called oxygenated organic aerosol, solid fuel combustion organic aerosol, and hydrocarbon-like organic aerosol. Generally, hydrocarbon-like organic aerosols are attributed to traffic. This is attributed to the solid fuel burning, and this could be because of several kind of sources, which certainly has become oxidized. And this type of information is difficult to obtain from offline methods. But you also see that across 3 sites, very interestingly, we see that OA, organic aerosol, generally is contributing more than 40 to 45%. And out of that, secondary organic aerosol has huge contribution up to half. So if you see half of organic, that is about 25% of total, is secondary organic. And if you add sulfate, nitrate, 10 plus 9, which is 20, and ammonium, which is 10. So you see 30% is secondary inorganic and 25% is secondary organic. So you see 55%, 50 to 55% of total PM2.5 in Delhi in winter time is secondary in nature, and getting them apportioned into sources is something which is of great interest in order to do something about sources. And offline methods just fall short in getting this information accurately and then getting them apportioned into sources. That was the summary picture what I just showed. Here what you also see for the two sides, what we are showing here, for out of those two sides, you can also get a time series. You see, this time series runs from 16 January 2018 to all the way up to 12 March. This is from 26 January to also 12 March at two sides, and each of really timely resolved fashion. So as I showed earlier, this is for OA, which is coming from traffic. This is one type of solid fuel combustion, we say one. Then there is another type of solid fuel combustion. This can be differentiated based on looking into their oxygen to carbon ratio and some other chemistry, which again can only be obtained from the online methods. And then likewise, you have semi-volatile oxygenated organic aerosol 1 and 2. And then you have this little volatile oxygenated organic aerosol, which is basically highly oxidized part of SOA. So what you see here is that you are getting these in terms of microgram per meter cube, and which each one, what is also shown is that you are trying to look at some independent tracer. For example, we are looking at either black carbon, which is coming from traffic, or black carbon, which is coming from wood burning. These tracers or nitrate and sulfate are expected to align or correlate well with these factors which you have got from the online speciation based, and then we have used here ME2, multi-engine 2 kind of receptor model to get this time series. Now the third thing what you see, contrary to the offline approaches where you would get just as a pie I showed for entire season, you are seeing here is that you could get on a daily and hourly basis that what is the contribution of various sources to PM2.5 for a particular time period. Here we are only showing for organics, but in subsequent slides I will also show that how you can combine organic and inorganic as well as metal information to get the full source apportionment, complete source apportionment of the total PM2.5. Okay, that was for winter. A similar work then we conducted over Delhi for summer. So what you see, this is the total information for PM2.5 sampled over summer using this 3 sets of instruments: a mass spectrometer, a real-time metal monitor, and athelometer. And you see, because of summer, you see contribution from elements is very high. It's up to 34%. Even in summer, organic contribution is 28, still high, but relatively lesser than winter. And black carbon certainly at IIT Delhi contributes significantly to PM2.5 all year long. And these are, of course, other kind of inorganic salts and chloride, etc. So then again, what we have done here is that we have tried to get source contribution to organics and then source contribution to metal. And subsequently now, we are now trying to combine these, which is part of a work which is under review. So what you see that, again, in winter, we could get these, how the time series of traffic sources are varying over time. Likewise for solid fuel. Now in summer, we got an interesting factor which was not seen before in Delhi. And so this you cannot get from offline methods, which is a cooking oxygenated aerosol. This source was resolved, very interesting, because you could get molecular signatures. The real-time approach enables you to get such kind of molecular information, which brings important fingerprint of some very specific sources. So one example here is that what you see, this C6H10O is a particular compound which is associated with cooking. That's how we could get that it is coming from this cooking related oxygenated aerosol. And likewise, if you look into elemental data, now we are looking at the data which is coming from exact. So now from that, you can get again very interesting sources looking at the metal data. So one is that we call it non-exhaust regular sources. That is, it is not coming from the tailpipe. It is rather from brake and tire wear. Okay, this is different from what comes from exhaust pipe. Now we can have a very clear information about dust. Okay, likewise, there is a chlorine-rich source. Then you can get an industrial source very clearly, carved out. Then you can get sulfur-rich, which could be either from spurious burning of coal or from coal power plant. That can be certainly be ascertained by looking into some other type of metals which bring important fingerprints of these sources. Okay. Now, what we also have done that time is that we tried to look into only wind information. Now, because you have a very tight time series, so you can combine that with the wind time series, and that can help you to get a very precise location of the source. That not type of source, but geographical location of the source as well. So what you see that for winter 2018 and winter 2019, we get these 3 kind of clusters for winter 18 and 2 kind of clusters are for winter 19, which have these type of basically sources which are available. So you see there are non-exhaust, solid fuel, sulfur, and then there are variety of these different combinations of metals. And these, each of combination actually refers to a very different kind of a source. Now, when you combine them with the wind information, what you see, this dot actually shows the receptor site, which is IIT Delhi. So see, one kind of source generally is coming from northwest, and the shade of the color shows how much is contributed. What is the contribution from the sources which are basically located in this corridor. Now see, cluster 2 shows that well, it is not only coming from northwest, but also some part is coming from this southeast as well. And you see cluster 3 has a very different spread. So this is another interesting information one could obtain by combining the wind as well as this very dense time series. This again shows that how the PM10 and PM1 data actually, PM10 sources, they vary during the cold period of 2018, cold period of 2018 here, and then common period of 2019. So you see, you can using this real-time data because you have data available every 15 minutes. So not only you can get good information about sources, it could also help you understand the chemistry which is going on at that time to get some better understanding of the sources, right? This is again an interesting work. What was done here is that a common period data, which was also available from Beijing and Krakow and Delhi, of both PM2.5 and PM1 metal from the exact was basically, arranged across 2 axes. One is PM2.5 to PM10, which tells you if this is 0, that means everything is crustal in nature. If it is 1, if you can understand, everything is coming from anthropogenic sources, correct? And on the y-axis, it tells you what is the enrichment factor, okay? So high the enrichment factor is that means that you have, compared to the crust, there is more and more contribution coming from anthropogenic sources, right? Okay. So for example, if something is lying here in this ring, this particular, box, which is 5, that means these are the ones which are highly impacted by anthropogenic sources. And that is what is shown here. You see, they are from variety of industries and combustion of non-wood fuels. And you see, if something is lying here, that means they are least impacted because this is very small and enrichment factor is small. And it shows PM2.5 ratio to PM10 is also very small. So these are all basically crustal in nature. So what you see that in a very consistent way across three very different cities, if you try to put this information in on two-dimensional axis, you can get these 5 groups which actually arrange themselves across these 5 major category of sources. And this information can help again policymakers in a significant way to understand the source and do something about it. Okay. So far, I have discussed mostly about the particulate matter. Now I'm briefly touching about now how do we do the source apportionment of volatile organic compounds. Volatile organic compounds we know are very important to one, understand their sources, and they also contribute significantly to the formation of secondary organic aerosol. So this source apportionment can again be done by sampling volatile organic compounds using PTRMS, which is a different kind of mass spectrometer. So this was done at 2 sites in Delhi, and then one in IIT Delhi, another is Manorashna. And if you just look into the second and fourth plot, it shows how different type of sources contributes to the volatile organic compounds at IIT Delhi and Manorashna. Basically, these are 3 from the original primary volatile compound, it has undergone oxidation. Second is something is coming from solid fuel burning, and third is traffic. Interestingly, if you look into traffic 2 and 1, you see the pattern at IIT Delhi and Manorashna is very different. You see that? Whereas Manorashna, it's almost there is no diurnality. At IIT Delhi, there is a strong diurnality because during winter time, there are some restrictions on movement of heavy duty trucks. And that is clearly shown that the way traffic 2, which is the gray area, light gray, is changing past midnight when the trucks are allowed to fly near IIT Delhi. So you could get these interesting information by doing such kind of source apportionment. So if I have to now summarize it, all the results, this is given in this summary picture, but you can see that total organic aerosol actually is coming from 1/5 of that from traffic, 1/3 from solid fuel, and 50% is secondary. If you look at total volatile organic compound, half of that is coming from traffic, and remaining half out of that, a big portion is coming from solid fuel, and a part is coming from secondary sources. That is, something is happening in the atmosphere. If you look for elemental PM2.5, largest contribution, interestingly, is coming from these halogens. This is very interesting, and we still are puzzled to understand where is that coming from: chlorine, bromine, and selenium. It is certainly coming from some combustion, but what is exact source is not known. And the second largest contribution is coming from non-exhaust, from the dust, and then followed by non-exhaust. So then you could also further look into these 4 major sources: OA, VOCs, black carbon, and element. For these 4 major kind of chemical species, one could try to apportion them into traffic, industries, solid fuel, waste burning, and secondary, and which are also, this information is given in this pies. By looking at that, you can actually get the summary picture of what is going on in the atmosphere of Delhi. Finally, this is my final slide. We have also used this real-time source apportionment to provide the source information when the COVID-induced lockdown was imposed in the country. So that time, this information was very crucial, and that because we had a real-time system running in Delhi, therefore, we could provide this information for all 3 major part of PM2.5, that is organic, inorganic, and black carbon for pre-lockdown, that is just before third week of March, and then during first phase of lockdown, second phase of lockdown, and third phase, because all three during that different level of economic activities were allowed to operate. So this information actually also was then published in the CPCB report. So with that, I will stop it here, and I hope you had a very interesting session. You liked it, and then hopefully you'll have lots of questions, and I look forward to a question and answer session. And at the end of slide, we have also all the list of references which were used to basically give this lecture. So thank you for your attention, and see you soon.